15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thank you for joining us on the podcast known as Space Nuts. This is episode 161, believe it or not. My name's Andrew Dunkley, and with me, as always, astronomer at large, Professor Fred Watson. Hello, Fred.
Hi, Andrew. How are you doing?
I'm well. It seems like weeks since we've spoken.
Oh, gosh, it does too, yes. And yet it's only weeks since we've spoken.
You've been on a little journey that's been exciting. We briefly mentioned it in the last episode that you were heading to South America to check out that amazing eclipse. Gee, I've seen some incredible photos. It looked just stunning.
It was, in fact. We saw it from a place called Vicuña, which is just inland from La Serena in northern Chile. La Serena is well known to astronomers because it's a place you fly to, basically, to use some of the big telescopes, which are just inland from there. So the eclipse path was directly through where we were located. Marnie had chosen well. The time we had was 2 minutes and 27 seconds of totality. That's the time when the moon was completely covering the disk of the sun. And it was truly spectacular. The corona of the sun, that white, mysterious outer atmosphere of the sun that's at a temperature in the region of millions of degrees. We don't really know how it gets that hot. It showed up beautifully, and it was actually quite elongated. The structure in the corona comes from the sun's magnetic field, and I think the magnetism of the sun was doing a grand job of elongating the corona.
Now tell me, how many people use their flashes to take photos?
Well, certainly not in our group, because we very quickly told them at the beginning, disable your flash.
Yes, pretty useless.
Perhaps the most memorable non-eclipse aspect of that eclipse, if I can put it that way, was that there's one road into Vicuña, and we were staying in La Serena, which is about 60 kilometres away. After the eclipse, we drove that 60 kilometres back to La Serena, and it took 6 hours.
Oh, my word. I've done one trip like that in Vanuatu.
Yeah.
We were travelling 11 kilometres, and it took 90 minutes.
Yeah, it was that sort of thing.
Yeah.
Except 6 hours of it is even more excruciating. It really was a nose-to-tail crawl because of all the people that were, watching the eclipse along that path of totality. But you don't really worry too much about that, because we kind of expected we'd have a late night, and we did. It was
well worth it, though. Well worth it. And this is my opportunity to invite all our Space Nuts audience to stay at my place in 2028 when we have a solar eclipse here in New South Wales, in Australia. It'll cross from the northwest, cutting across my locality right here. We'll be only 40 kilometres from the dead centre of the shadow, and then it will black out Sydney. It's going to happen about 1 o'clock in the afternoon in July of 2028. So the invitation's open. I've got a few spare beds.
Be careful what you wish for, Andrew. You might get all 5 of our listeners coming to stay with you.
Yes, and that could be a problem. They might have to share. Now, today, Fred, we're going to be talking about something exciting. Australia's CSIRO has found the source of a fast radio burst.
Fast radio burst. That's right.
Radio burst. NASA is planning to go back to Titan because they left the keys to the spaceship there last time. And Ralph has sent us a question that you wanted to tackle about light echoes. We'll look into all of that. And one more thing, Fred's got a double whammy. If he sounds a little bit off the chart today, he's got a cold, and that's sort of not being helped by jet lag. So please forgive Fred He's going to struggle on, and we really appreciate it.
I'll struggle on. Don't worry, we'll get there.
Now, Fred, the CSIRO, Australia's science body, has found the source of a fast radio burst. I'm pretty sure they wouldn't be the only ones looking, but it sounds like they've hit the nail on the head.
That's right. In fact, it's a really interesting piece of science, this, because these fast radio bursts, we still don't understand where they come from. They are completely unpredictable. You get a burst of radiation of radio waves that lasts somewhere in the region of 3 to 5 milliseconds, thousandths of a second, which is why they're fast. And of course, they're in the radio spectrum, which is why they're radio bursts. So these things have been now known about for a decade or so. And the hunt is on to try and find out what it is that causes them, because there are certainly ideas as to what might be happening, but we don't have any certainty about it. So a first step in doing that is to try and localize one of these things when it happens and see whether it is in a galaxy, for example. We know that they, from various considerations, we know that they're at what you might call cosmological distances. They're not in our galaxy or even the local group of galaxies or the local cluster. They are in deep space. Their distances are measured in billions of light years. We know that because the signal itself undergoes something called dispersion. You get it's almost like, the spectrum of light being broken up. White light can be broken up into a spectrum. Mm-hmm. Radio waves can likewise be broken up into a spectrum. And it turns out that the high frequency ones arrive earlier than the low frequency ones. And by measuring that dispersion, the time delay, you can tell roughly how far away you're getting this signal from. And they're all basically at these large distances, the billion light year plus distances. I think one or two have been slightly less than that, but most are plus. So, okay, the history of the story is that so far about 80 of these things have been measured. It was one for a while. It's now more than that. One turned out to be a repeater. It was the same thing going off multiple times, spread over a period of years, actually. We believe that there are now about another 5 of these that have been seen to repeat, but most of them are just one-offs. So that immediately it presents a puzzle, because if it's a one-off, you can say, well, this is an enormous amount of energy being released by something coming to a cataclysmic end at the end of its life. But that doesn't fit the bill for the repeaters, because you can't have a cataclysmic ending and then another one and then another one. So we might be talking about 2 completely different phenomena here. Why is this in the news again? It's because, certainly as far as the CSIRO is concerned, there's been a major triumph in pinpointing exactly where one of these things is. And it comes from data measured, with the Australian Square Kilometre Array Pathfinder, or ASCAP, because the group that are doing this work have been using ASCAP in order to search for fast radio bursts. They've got very clever algorithms that allow the Australian Square Kilometre Array Pathfinder to look at a reasonably wide area of space, but also to home in on exactly where one of these things has gone off when they find a fast radio burst. And the major triumph here is that they've now located one with an accuracy of 1/10 of an arc second. That's a phenomenal accuracy. Remember, an arc second is 1/3600th of a degree. So a tenth of an arc second, of course, is 1/10 of that. It's a tiny, tiny angle.
That's brilliant.
But by doing that, it means that you can, once you know the exact position of one of the radio bursts, you can look in visible light in the optical spectrum to see whether it matches the position of, for example, a galaxy. And in this case, that's exactly what has been found. it has been found to match a galaxy, you'll love this, Andrew, whose name is DESJ 514425.25 minus 405 400.81. That's its name.
Cool.
Which turns out to be the host galaxy of a fast radio burst with the name of FRB 180924.
Right, and no truth to the rumour that it was Mayday, Mayday, this is Will Robinson on Jupiter 2.
That's quite true. There is no truth whatsoever.
No truth whatsoever to that.
It means that this thing has been found to be in a galaxy. It's not actually in the middle of the galaxy either. It's somewhere in the outlying area of this galaxy with that long-winded name I just mentioned. Which, by the way,
call it DES.
DES, yeah, that's good. DES is Dark Energy Survey, by the way, just in case you want to know. So it's been very accurately pinpointed to be about 13,000 light years from the centre of this galaxy. That in itself is interesting because you expect these highly energetic events like fast radio bursts to come from the central, highly, what you might call highly congested regions of galaxies rather than the outlying, rather suburban, outer extremities. Where the density of objects is much lower. So an interesting puzzle there. Now, that's in itself a major discovery, and certainly is a big, it's a feather in the cap of this team, the CSRO team, using the ASCAP telescope. But it came only days before another discovery was announced, this time by a group doing the same sort of work in the United States. So Caltech, which runs the Owens Valley Radio Observatory, or OVRO, they caught a burst earlier this year, in fact in May. It's called FRB 1905-2023, and they've used the Keck Observatory in Hawaii, which is an optical observatory, to essentially do the same sort of trick, to identify the galaxy in which this fast radio burst took place. And sure enough, once again, it aligns with a galaxy. It doesn't have quite such a complex name. The galaxy itself is, I think it's pretty, it will have a name, but it'll be just the position of it. And I think the fast radio burst itself is basically coming into, once again, the galaxy itself, but not as well localized. I'm trying to choose my words carefully here because ASCAP has the accuracy, the pinpoint accuracy to tell you exactly where in the galaxy this thing has been found, whereas the Caltech group are not at such a high precision. So they can't say, well, it's 13,000 light years from the center of the galaxy or things of that sort. Right. Nevertheless, it does demonstrate that, once again, these fast radio bursts are within the confines of a galaxy itself.
So, long story short, we have pinpointed a couple of sources, one very accurately, but we still don't know why.
Yeah, that's right. But I think, when you're faced with a big mystery like this, clearly the theoretical physicists can build models of what might be going on here, colliding neutron stars or whatever it is that you think these things might be. But the way to perhaps explore what's happening is exactly what's going on now, to try and get multi-wavelength observations, to bring all the resources of astronomy to bear on the problem. And in particular, if you can identify galaxies that host these things, and then if you can identify that these galaxies all have some common peculiarity, that might give you an insight. And one peculiarity might be that the galaxies have been involved within the last billion years or so in a collision, for example, something of that sort, with another galaxy. If you could say, well, all fast radio bursts come from galaxies which have gone through some kind of traumatic experience in recent times, i.e. the last billion years or so, then that might offer you some kind of handle on what's causing the FRBs.
Well, I suppose, given that we recently talked about galaxies sharing radio waves. I think that's what it was.
That's right. Yes,
I suppose if they collide, then some may impact and cause this to happen. Who knows?
Yeah, that's the kind of thinking. Exactly that.
Okay. Well, watch this vast space. Maybe there'll be more to learn very soon about these fast radio bursts. You're listening to Space Nuts. Andrew Dunkley here with Fred Watson.
0G, and I feel fine.
Space Nuts.
Now, Fred, we turn our attention to NASA and their plan to go back to Titan. Now, there's probably a very good reason for this. Losing the car keys may not have been it, which I mentioned earlier, but we might have to start by talking a bit about Titan and why we were there before, and then why we're going back.
Yeah, I think Titan is, apart from the Earth, one of the most interesting places in the entire solar system, because it's a moon of Saturn. It's Saturn's biggest moon. It's the second largest of all the moons in the solar system. The largest is Jupiter's Ganymede. Titan, though, is bigger than the planet Mercury, so it's a large object. It's not, a trivial thing. Of course, the thing that makes it interesting is that it's got this atmosphere, this smog-like atmosphere that is impenetrable to visible light, just about penetrable to infrared radiation, and of course transparent to radio waves, which is how we know what the surface is like, because the Cassini spacecraft, which was in orbit around Saturn for 13 years until 2017, that was able to map much of the surface of Titan using its radar, aperture synthesis radar that was on board Cassini. In fact, they flew by Titan 126 times during the Cassini mission and gave us maps of Titan. Of course, what makes Titan almost unique? It's unique if you discount the Earth. It is the only place in the universe where we know there is liquid in equilibrium with its atmosphere, liquid surfaces. And those liquids are not water as they are here on Earth. They are hydrocarbons. They're liquid natural gas. So it's a mixture of ethane and methane in these lakes, which are predominantly near the North Polar region of Titan. They're in Titan's northern Arctic. The biggest of them, the three largest, are monumental. In fact, the biggest of them is 3 times the area of the biggest freshwater lake on Earth, which is Lake Michigan, Huron. So they're big. And they are, as I said, they're made of liquid hydrocarbons, extraordinary stuff. They sit in depressions in the surface, but the surface is not made of rock. It's made of solid water ice, which is rock hard. A very, very interesting world. And then you've got this thick...
So that suggests it's cold.
It's minus 190 or thereabouts, the surface temperature.
Oh.
So...
It's a bit like where we are at the moment.
Yes, well, that's right. But you can turn on a heater. If you turn on a heater on Titan, the rock melts because the rock is made of ice. So, yeah, tricky stuff. So the thing about Cassini is that so much was learned about Titan that scientists really grabbed hold of the idea that this is one of the most interesting and provocative in some ways place in the whole solar system to explore again. And so there have been a number of proposals to NASA suggesting repeat visits to the Saturnian world, and in Titan in particular. Whole different range of things have been proposed, ranging from balloons to float in Titan's atmosphere, to submarines to have a look underneath the surface of these oily seas. And one of those projects has now got the go-ahead, which is fantastic news. It's a project called Dragonfly. And Dragonfly is actually a drone. It's
I was going to say that.
Yeah, well, you were right. with a name like Dragonfly, it could be anything else, really, could it? Oh, if I'd said a Dragonfly is a submarine, then you might have thought.
Well, no, because I would have thought, okay, dragonflies do land on the water.
They do. Yeah. They don't do well underneath it.
No, they don't.
So Dragonfly has 8 rotors. It's a pretty standard but probably quite large copter drone. 8 rotors arranged in pairs apparently, so that you've got some redundancy within the mechanism, and it actually is going to have a small radioisotope thermal generator on board, which will provide the power. So this is a little packet of plutonium, probably, and the standard RTG, radioisotope thermal generator, is about 13 kilograms, I think. This might be a bit less, I'm not sure. But that will power the Dragonfly, and they're hoping that it will have a range measured in tens or possibly hundreds of kilometers. So it will be able to sample different places on Earth, on Titan, looking at different molecular structures in the atmosphere of Titan and on the surface of Titan. So in particular, the scientists, these are scientists who are interested in life precursors, the fact that, Titan has got interesting molecules whose size are about the size of proteins, but whose nature is unknown. Those were detected by Cassini, because Cassini could, do the sort of physical measurement of things, but it wasn't equipped to have any kind of biological sensors because nobody expected anything like what we found when Cassini got to the Saturn region. So Dragonfly, I think, is meant to be a multi-purpose aerial explorer on Titan, which will look at some of the really interesting regions. One of the things that excites scientists, astrobiologists, and others is the dune. There are dune fields on Titan, and the dunes are actually made of a mixture of ice crystals and hydrocarbons.
Wow!
If you want to find out whether there's any kind of living organisms, that's one of the places to look. The sand grains are, organic matter, rather than the sort of sand that we find here on Earth, the dust grains, if I can put it that way, that will be found in these dune fields. There is a crater as well where the scientists who are proposing Dragonfly want to have a close look. It's a 50-kilometer impact crater. It's called Selk. And the suggestion there is that because it's an impact crater, the heat of the impact would melt the ice of the surface of Titan and allow it to mix with the organics and maybe give you the building blocks of life. They want to look very closely at this crater, Selk. So Dragonfly, very, very interesting project, scheduled for launch in 2026. Unfortunately, it takes quite a while to get to Titan, so it's going to be 2034 before it touches down. I don't know whether you and I will still be going there, but hope we are.
I do too, gosh.
Because I want to talk about this.
Yeah, I'm excited to see what they see. I'm also wondering how they're going to navigate up there. Is it going to be pre-programmed? Is it going to be automated and figure its own paths out and its own control? I suppose the technology will exist, so it's probably not that difficult a task in
No,
some
that's
respects.
right. It's got to be autonomous at some level, Andrew, because for the same reason that the Mars rovers are at least partly autonomous. That's because the signal time backwards and forwards between Mars and the Earth is significant. It's measured in minutes. It's even longer in the case of Saturn. So Dragonfly clearly has to have its own artificial intelligence that's going to tell it what to do and how to respond to different environmental circumstances, and without human interaction, because the delay in getting that human interaction is going to be far too long. Very, very challenging technology, but really interesting stuff.
Yeah, and I like the idea of a drone on another world because we haven't done that yet, have we?
No, we haven't. And
So.
let's face it, that's where drones belong, really, isn't it?
Yeah, I'm pretty sure you see them all over the place now. And
You do.
it's still a bit disconcerting. I was out in the backyard the other day and I heard this weird noise and I looked up and this massive drone just came straight over the top of the house. And I thought, yeah, I can see why people are getting a little bit upset about their invasion of privacy because I want to know what it was doing.
Yes, that's right. We had drones watching the eclipse. I'm not quite sure what they were doing either.
Anyway,
Probably watching
exciting
the people
times
watching the eclipse.
heading
Yeah.
back to Titan in
It's good.
in the sort of not too short-term future, but I'm sure there'll be more to talk about as that gets closer. This is Space Nuts. Andrew Dunkley here, Fred Watson there.
Roger, you're loud and clear here also.
Space Nuts.
And we're back. Now, before we get on to our question, just reminding you that we are on YouTube. In fact, Hugh, our producer, has been very busy getting our YouTube channel all smished up so that it looks a little bit more like a YouTube channel. So youtube.com/c/Space Nuts is where you'll find our YouTube channel. With all our back episodes available. And he's done a great job to tidy it up. It actually looks semi-professional. And thanks again to all our patrons who are signing up in their ones. We've got 23 patrons who are putting a couple of dollars here and there into Space Nuts to keep us afloat on Titan. And we really do appreciate your support. And if you would like to do the same, you can do so at patreon.com/spacenuts, patreon.com/spacenuts. Now, Fred, we have a question from Ralph Haney in California. G'day, Ralph, and thank you for sending us in your question. He says, hello, professional space nuts. I don't know any professional space nuts. But anyway, a while back, Professor Watson spoke of an interesting phenomenon called light echoes. These were reflected light particles received on Earth long after the initial event. For example, a supernova, according to Dr. Watson's explanation, these light echoes give us a glimpse into the nature of the star stuff involved in the original event. Here's my question. With so many light echoes bouncing around out there, how do you differentiate between them? How would you know, for example, that echo E123 is from the supernova event of 1842 out of the Pisces constellation? Grateful nut, as always, Ralph Haney. Thank you, Ralph. Great question.
It is a good question. And, you know, it's well posed as well. It's very nicely put. So just to clarify, a light echo is when you've got some kind of outburst, and it doesn't have to be a supernova, although that's really specifically what Ralph is talking about here. But there's a few objects where you've got a star, an unstable star, in the center of a cloud of dust, and it has an outburst. The star lights up much more brilliantly than it has been and then fades away. And that pulse of light sort of radiates outwards into the surrounding dust and lights up the dust in different ways. There's a very famous example in the constellation of Monocerotis. Yes, that's it. The unicorn. Sorry, I'm still suffering from jet lag brain here, and that's exactly what we see. You can actually see time-lapse images of that, which have been put together by, I think, NASA and probably the European Space Agency as well, from Hubble telescope images. Which shows this expanding shell of light illuminating the dust cloud around the outburst star. But I think what Ralph's talking about here is, in some ways, the more interesting aspect. And that is, if you have a supernova explosion that gets very brilliant for a number of weeks or months and then fades away, and that pulse of light radiates from the supernova in all directions. Sometime after the original explosion, it might well illuminate a cloud of dust, which is quite a long way from the supernova. And so you get this light echo that appears and then disappears because once again, it's a short pulse of brilliant light, and it's only lighting up the dust cloud for a short time. So how do you know which lit up dust cloud belongs to which event? And there's two parts to the answer. One is these things are not that common. There's only literally been a handful of supernova light echoes that have been observed. Perhaps the best known is Tycho Brahe's supernova of 1573. I'm just making sure I'm thinking the right thing. No, it's actually Kepler's supernova. Kepler's supernova of 1604. That went off in 1604, was observed by Kepler, but it was observed again because of the light echo only a few years ago by big modern telescopes on Earth. And of course, getting the same light, although it's come on a dogleg path, means you can throw the whole inventory of modern equipment to try and analyze it. And that's what happened with Kepler supernova. So my point is that there really have only been a handful of these. So they're not bopping off everywhere in the universe. They might be in the universe, but in our galaxy, supernovae are relatively rare. And this only works at distances which are measured in, tens or hundreds of, thousands or hundreds of tens of thousands of light years, that kind of distance. So there are not many of them. On average, you get one supernova per 100 years in any galaxy. That's on average. We're actually overdue for another one now because it's 400 years since we had one in our own galaxy. Apart from the ones that, actually, we've talked about this before, some are hidden behind dust clouds, so we didn't see them.
That's right.
Anyway,
there was a report about us missing.
We did, yeah, that's right. Sorry, that's just another digression. So first of all, there aren't too many of them. But the second point is perhaps the more important one, and that is that the geometry of these light echoes is very precisely understood. So if you envisage two clouds of dust being lit at the same time by a light echo, then the fact that they're both appearing at the same time tells you something about where they are in terms of their three-dimensional distribution of space, because it turns out that there is actually an ellipsoidal surface. If you imagine the supernova, at the focus of an ellipse, let's think in two dimensions. Let's imagine it being an ellipse drawn on the sheet of paper. An ellipse has two foci, one at each end of it. You plonk your supernova at one end. Excuse me. Anything lying on that ellipse will produce a light echo at the same time on the Earth, which is actually at the other focus in the ellipse. I'm getting into technical stuff here, but it's just to explain that the geometry is such that you can understand the way these light echoes behave. Because in particular, if you see a cloud of dust and you know how far away it is, then you can be very precise in the timing of the light echo. In other words, you see a light echo, it's on a dust cloud whose distant then you know that the light echo came from the supernova event of 1842, for example, that Ralph is speaking about.
So let's just say for a moment, there is a supernova tomorrow.
Yes.
And it lasts a few weeks and then it fades away. But we know there's a dust cloud at point B.
Yep.
Which that light will ultimately bounce off and we'll see it again. Would we be able to predict when that second light appearance would happen?
Yes, and indeed exactly that has happened already. That's been done with one of these light echo events. I can't remember which one, but that was, they saw a light echo from a dust cloud, and the prediction was, well, this other dust cloud is nearby. There's going to be a 5-year gap or something. I can't remember the details. I'll have to look that up. But that has happened already, that predictions have been made, and I think they turned out to be correct.
Wow. Gosh. I'm feeling very proud of thinking of that.
Yes, you're a good lad. That's why That's why you and I talk every week.
Well, I must be learning something, Fred. There you are.
No, but it's a good point. That's absolutely right. That you could predict them if you know the distance to the supernova or whatever it is, and you know the distance to the dust cloud. You can make a prediction about when it will light up.
Fantastic. All right. Hopefully we've answered Ralph's query about light echoes. And thanks again for the question. And we got a whole bunch of questions while you were away, Fred. So I think we're going to have to probably dedicate an episode to knocking a bunch of these off. So that
I think we should, Andrew.
But it won't be next week.
Do you mind? Sorry, go on.
No, I was going to say it won't be next week because I think we're going to be focusing pretty heavily on something that happened 50 years ago. Someone stubbed their toe on a rock somewhere.
Something like that, yeah. Just forgive me, just going back to Ralph's question briefly. I meant to say this at the beginning. And this is an unashamed plug, but a book called Cosmic Chronicles with a title... written by an author with a name very similar to mine, will come out in October. Cosmic Chronicles, a user's guide to the universe, and it has a chapter on light echoes. So for Ralph's benefit, that's the one to look out for, because it will also be published in the United States of America. There you go. That's the plug. Sorry about that.
All plugs are welcome. Thank you, Ralph, for the question. Really appreciate it. And thank you, Fred, as always. And I hope you get well soon.
So do I, yes. I'm looking forward to speaking next week when hopefully I won't sound like I do today.
Well, we appreciate the effort and you always sound great to us. Thanks, Fred. We'll talk to you soon.
Sounds great. All the best. Thanks again.
Professor Fred Watson, astronomer at large, and from me, Andrew Dunkley, thanks as always for listening, and please send us your feedback, even if it's not a question. We do love to hear from you, and we'll catch you next time on another edition of Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes and Stitcher or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.